Continuing with our theme of wanting to be able to take the Laplace transform of increasingly complex situations, complex functions, we're going to talk about some more operational properties, particularly one about derivatives of a transform again. So if I take the derivative of some Laplace transform, capital F of S, what I'm doing is I'm taking the derivative of an integral from 0 to infinity of e to the negative st f of t dt. That's just by the definition of the Laplace transform. Well, you might remember from calculus that it doesn't actually matter whether we integrate or take the derivative first. We can interchange those under most circumstances, and so we're going to interchange those and instead take the derivative before we integrate. So taking the derivative with respect to s of e to the negative st f of t dt results in us having negative t e to the negative st f of t dt to take the integral of. Well, what this is just the Laplace transform of negative t f of t, and we can pull the negative out front, so it's really the negative Laplace transform of t f of t. Well, this gives us insight into the idea of being able to take the Laplace transform when we have powers of t multiplied by some function of t. So we have a theorem about derivatives of transforms. If we have the Laplace transform of some function of t that we are going to denote capital F of S as is our tradition, and n equals 1, 2, 3, really any number you want, then the Laplace transform of t to the n f of t is going to be equal to negative 1 to the n times the nth derivative with respect to s of your Laplace transform. So let's take a look at how that applies with an example. We're going to look at taking the Laplace transform of t sine of kt. Now you might note that if we were to take this transform using the definition of the Laplace transform, we'd have some integration by parts to deal with, and we'd have like 3 different functions going on, so it would take multiple iterations of that. It'd just be a pain. So instead, let's use this theorem to help us out. So we need something in the form t to the n f of t. Well, we have t obviously out in front, and it's unwritten, but it's raised to the first power. And then we have the sine of kt. That's a great choice for f of t here, right? And we already know that the Laplace transform of this f of t that I've identified, so the Laplace transform of sine of kt, we already know that from a previous theorem to be k over s squared plus k squared. So this is going to function as our capital F of S. So now that I know that n is 1 and I know what capital F of S is, then I'm ready to apply the theorem to find the Laplace transform of t sine of kt. It needs to equal negative 1 to the nth power, so to the first power, times the nth derivative, so the first derivative, so dds, of f of s. And I said f of s is going to be k over s squared plus k squared. So negative 1 to the 1 is just negative 1. And then all that's left for me to do is take the derivative of k over s squared plus k squared. And when I do that, I'm going to get negative 2ks over s squared plus k squared, the quantity squared. And that's all from just simple derivative stuff that we already know. So now, when I multiply -1 times that, I'm going to get 2ks over the quantity s squared plus k squared squared. And that's all there is to it. We now know the Laplace transform of that product.